Learn how the most ambitious high-speed rail system in America is being built from the ground up. Here was born the largest infrastructure project in the United States. 119 miles of active construction stretch across California's Central Valley. 58 completed structures now stand where farmland once dominated the landscape. Over 80 miles of finished guideway await the trains of tomorrow. This is California high-speed rail, and this is how it's being built. On January 6, 2015, construction crews broke ground in Fresno, California. They began a project that would cost over $100 billion when complete. The full system will span 494 miles from San Francisco to Anaheim. Trains will reach speeds of 220 miles per hour. And this engineering marvel will transform transportation across the Golden State. Over 16,000 jobs have been created since construction began. More than $25 billion in economic activity has been generated. Revenue service is targeted for January 1, 2032. Let's explore every stage of this incredible construction journey. 4 massive construction packages divide the 119 miles of work. Construction Package 1 covers 32 miles from Madera to South Fresno. The Tutor, Perini, Zachary, and Parsons joint venture leads this section. Their original contract was $985 million, now exceeding $2.4 billion. Construction Package 2 and 3 span 65 miles from South Fresno to the Kern border. Dragados and Flatiron, a joint venture of Spanish and American companies, builds this section. Construction Package 4 covers 22 miles and became substantially complete in 2024. California Rail Builders, a joint venture of Spain's Ferrovial and Griffith Company, delivered this milestone. Up to 1,700 workers report to construction sites daily, or they work across more than 30 active locations throughout the Central Valley. The design ecosystem brings expertise from around the world. WSP produced the 1,400-page design criteria manual guiding all construction. AECOM now leads the program management support team. Sistra and TIPSA won the $131 million track design contract. Foster and Partners and Arup are designing the futuristic stations. The Central Valley alignment crosses the San Joaquin Valley floor. This flat agricultural terrain sits on deposits of clay, silt, sand, and gravel. Rock lies approximately 6 miles below the surface, so no rock excavation is needed, but 3 major geotechnical challenges dominate the construction process. Land subsidence is the most significant problem engineers face. Decades of groundwater pumping for agriculture have caused the ground to sink. In some areas, the land drops up to 1 foot per year. This forced over $100 million in change orders for elevated embankments. Expansive clays with high shrink-swell potential require special soil treatment. Corrosive soils demand protective coatings on all buried metal structures. Before construction begins, contractors prepare detailed construction management plans. Agricultural land is cleared of crops, orchards, and all improvements. All vegetation, debris, stumps, and roots are removed down to bare mineral soil. Topsoil is stripped and stockpiled for later restoration of the land. Geotechnical investigation uses boring programs and advanced testing methods. Standard penetration tests and cone penetration tests analyze the soil. Excavation proceeds with hydraulic excavators, scrapers, bulldozers, and haul trucks. At one underpass alone, 41,000 cubic yards of dirt was excavated. Over 1,800 utility diversions are required across the construction packages. More than 15 rivers and creeks intersect the alignment and must be managed. All California high-speed rail structures are designed for a 100-year service life. 4 foundation types support the massive structures rising across the valley. Cast-in drilled hole piles are the primary deep foundation for the project. These piles range from 18 inches to over 20 feet in diameter. Some extend to depths exceeding 250 feet below the surface. An auger drill rig bores the hole through the valley floor soil. If groundwater is present, bentonite slurry stabilizes the walls of the hole. Ironworkers assemble massive rebar cages on site before installation. Cranes lower the pre-assembled rebar cages into the drilled holes. Concrete is placed through tremie pipes from the bottom up. Quality is verified through cross-hole sonic logging and gamma testing. At the Hanford Viaduct, nearly 7,000 production piles were driven. ICEI 46. Diesel impact hammers pound the piles deep into the earth. Spread footings are used where solid-bearing soils exist near the surface. At the Wasco Viaduct, individual footing pours consumed nearly 290 cubic yards. Foundation concrete achieves 3,000 to 6,000 pounds per square inch compressive strength. Pre-stressed elements reach over 8,000 pounds per square inch for maximum stiffness. This high-strength concrete handles the severe vibration at 220 miles per hour. All rebar meets ASTMA 615 grade 60 specifications with 60,000 pounds per square inch yield strength. The foundations form an invisible but critical base for everything above. The viaducts are the visual signature of California high-speed rail. Massive concrete elevated structures carry 2 tracks above the farmland. They soar over freight corridors, rivers, and highways of the Central Valley. 5 distinct structural types are used throughout the construction. Cast-in-place post-tensioned concrete box girders form the primary structural type. These feature a concrete box measuring nearly 9 feet deep by 43 feet wide. Typical span lengths reach approximately 100 feet between supports. Temporary falsework towers of steel pipes support the construction. Formwork is placed, rebar is tied, and post-tensioning ducts are installed. After curing, high-strength steel tendons are threaded and stressed with hydraulic jacks. The precast concrete girder pergola structures are the most distinctive innovation. These massive platforms carry high-speed rail directly over active freight tracks. BNSF and Union Pacific trains continue operating below without interruption. Enormous precast girders sit on concrete edge beams 8 feet wide by 15 feet tall. Some tub girders weigh over 450,000 pounds each. These are among the largest tub girders ever precast in North America. At the San Joaquin River Viaduct, each of 198 girders weighs 156,000 pounds. Large crawler cranes lift each girder into position on the edge beams. Transverse diaphragms are cast to tie the girders together. The 43-foot wide deck slab is then poured over metal decking. And cast-in-place concrete arches provide dramatic, aesthetic landmarks. The San Joaquin River Viaduct features a 210-foot double-arch span. This is designated the Northern Gateway into Fresno. The Cedar Viaduct showcases 2 pairs of double arches spanning 179 feet each. These arches rise nearly 40 feet tall and are visible from State Route 99. A tied arch bridge spanning 249 feet is under construction near Hanford. The completed viaducts present a monumental, clean concrete aesthetic. Smooth grey surfaces show natural Portland cement finish with no paint. Columns stand at 100-foot intervals, supporting the massive deck above. The 43-foot wide deck stretches flat, awaiting track and catenary wires. The Fresno River Viaduct was the first permanent structure built. Construction began on June 16, 2015, marking a historic milestone. It stretches 1,600 feet and stands 25 feet above ground. The viaduct crosses Route 145 and the Fresno River below. The San Joaquin River Viaduct is nearly a mile long at over 4,700 feet. It features the signature double arch span over the river. This structure won Structure Project of the Year 2020 from the California Transportation Foundation. The Cedar Viaduct stretches 3,700 feet through the valley. It consumed 8.6 million pounds of steel rebar. Over 37,000 cubic yards of concrete were poured into this structure. 40 precast girders were placed over State Route 99 during nighttime closures. The Hanford Viaduct is the largest high-speed rail structure in the Central Valley. It stretches 1.2 miles long with 978 precast girders. 286 columns support this massive structure. Over 40,000 cubic yards of concrete were placed during construction. The Wasco Viaduct was completed in 2024. It includes a 375-meter pergola spanning over BNSF tracks. This structure was designed for speeds of 220 miles per hour. All structures meet California's stringent seismic requirements. A two-level earthquake design ensures no collapse under extreme seismic events. Up to 5 feet thick for maximum, up to 5 feet thick for maximum protection. They run for thousands of feet where the two rail corridors parallel each other. At the Conejo Viaduct, the barrier required over 12,000 cubic yards of concrete. These barriers protect high-speed trains from any freight train derailment. Parapet and derailment walls line both edges of every elevated deck. These safety features ensure trains stay on the guideway at all speeds. The completed guideway appears on satellite imagery as a continuous strip. New concrete construction crosses the valley through agricultural fields and roads. But the structures are dramatically larger than typical highway overpasses. They represent a new scale of infrastructure for American transportation. Every safety feature is designed for trains traveling at 220 miles per hour. No detail is too small when protecting passengers at these speeds. The combination of barriers creates an unmatched safety system. The only below-grade section runs through downtown Fresno. The Fresno Trench extends approximately 2 miles through the city center. It runs from Olive and Belmont Avenues to Stanislaus Street. This top-down construction reaches 40 feet deep at typical sections. Where the rail passes under State Route 180, it reaches 80 feet deep. Workers dig from the surface, constructing the tunnel section as they go. Shotcrete is sprayed with rebar mesh as excavation progresses. The highway is reconstructed above once the tunnel section is complete. This section eliminates 20 level crossings between Madera and Fresno. No longer will traffic stop for trains at street level in Fresno. The trench represents sophisticated urban construction techniques. It minimizes disruption to the downtown area during construction. Workers coordinate carefully with existing utilities and infrastructure. The finished trench will be invisible to those driving above. Trains will glide silently beneath the busy streets of Fresno. The mountain crossings represent the most demanding portions of the project. Approximately 50 to 54 miles of tunneling will pierce 3 mountain ranges. The Pacheco Pass crossing connects San Jose to Merced through the mountains. This section includes a 1.6-mile tunnel through difficult terrain. A 13.5-mile tunnel will become the longest intercity rail tunnel in America. These will be twin-bore tunnels with 28-foot internal diameter. Each tunnel carries a single track in one direction. The geology is formidable, featuring deformed and metamorphosed rocks. The tunnels cross the Ortigalita fault zone, adding seismic challenges. Hazards include ground instability, methane gas, and significant groundwater. The cost for the Pacheco tunnels alone is approximately $5 billion. The Tehachapi Mountains require 9 tunnels totaling nearly 11 miles. These tunnels range from 0.3 to 2.5 miles each. The alignment climbs from 404 feet to over 4,000 feet elevation. Oil and gas fields and multiple fault zones add complexity. The Palmdale to Burbank section is the tunneling marathon of the project. 4 tunnels total nearly 28 miles through the San Gabriel Mountains. The deepest sections reach over 2,600 feet below the surface. Groundwater pressures exceed 725 pounds per square inch at depth. Tunnel boring machines will be the primary construction method. Each machine costs upward of $50 million. The mixed geology may require specialized variable density boring machines. Its shorter sections use the sequential excavation method with shotcrete and rock bolts. Cross passages between twin bores are excavated every 800 feet. At active fault crossings, engineers have designed special fault chambers. These oversized sections can accommodate over 6 feet of seismic displacement. Track can be realigned after an earthquake within these chambers. An early earthquake detection system will stop trains before major shaking arrives. This system is modeled after Japan's proven Shinkansen technology. Seismic detectors will be placed at regular intervals along the entire route. The Dragados Flatiron Precasting Yard near Hanford is an industrial marvel. This 40-acre open-air facility features 14 casting points. Up to 100 workers manufacture concrete elements at massive scale. Nearly 2,400 California wide flange girders have been produced. These girders range from 54 to 151 feet long. Some weigh up to 185,000 pounds each. 90 tub girders have been cast, some weighing 500,000 pounds. These are among the largest precast concrete elements in North America. 60,000 deck panels have been manufactured at this facility. 12,000 piles were fabricated for the foundations. Peak production weeks deliver 8,000 linear feet of pile. 5,000 linear feet of girders are cast in a single week. 8,000 square feet of deck panels roll out during peak production. A Vince Hagen portable batch plant mixes the high-strength concrete. The BHS twin-shaft mixer produces self-consolidating concrete. Formwork from Helsa Industries creates 600-foot casting beds. Hamilton Form Company provides specialized deck panel forms. 300-foot girder beds allow for the longest elements. The yard operates like a precision factory in the open air. Every element is manufactured to exact specifications for installation. California High-Speed Rail has selected ballasted track as the primary system. The authority purchased over $500 million in track materials. European norm specification ballast will support the rails. Direct fixation slab track is reserved only for tunnels. The rail will likely be UIC 60 profile, the standard for high-speed systems. Rails arrive as continuously welded rail in strings over 1,400 feet long. Specialized multi-car rail trains transport the rails to the construction site. Rails are unloaded at walking speed using guide rollers every 39 feet. Pre-stressed concrete ties are spaced at 24 inches center to center. Each tie weighs approximately 630 pounds. Ties measure about 11 inches wide, 9 inches high, and 8.5 feet long. Elastic rail fastening clips secure the rail to each tie. These provide constant pressure and electrical insulation. Elastomeric pads attenuate vibration at high speeds. Sub-ballast is placed first, 6 to 8 inches of graded crushed stone. Initial ballast is added in 4 to 6 inch lifts. Concrete ties are distributed at precise design spacing. Rail is placed onto ties with temporary fastening at every third tie. Clips and insulators are installed at every tie position. Additional ballast brings the track to full profile depth. Initial tamping levels and aligns the track precisely. Rail alignment tolerance is plus or minus 1 millimeter for high speed. Rails are stressed to neutral temperature between 95 and 110 degrees Fahrenheit. Field welding joins rail strings using thermite welding at 2,500 degrees. Final ballast and multiple tamping passes complete the track installation. Track geometry requirements for 220 miles per hour are extraordinarily precise. The minimum curve radius is approximately 22,000 feet. This allows trains to maintain speed through curves without discomfort. Maximum super elevation reaches up to 7 inches on curves. Track gauge is standard 1,435 millimeters. Gauge tolerance is plus or minus 1 millimeter across the entire route. Minimum track centers measure 14 feet on straight sections. Additional widening is required on curves for safety clearance. The maximum gradient is 3.5%. The steepest section through Tehachapi reaches 2.8%. Plaza and Thura machinery will install and maintain the track. The Dynamic Tamping Express handles 3 ties simultaneously. The ballast regulator shapes the crushed stone profile perfectly. The dynamic track stabilizer settles the track into its final position. Track geometry recording vehicles verify every measurement. A new 150-acre railhead facility was completed in Kern County. This southern railhead connects to the National Freight Network, 10 miles of temporary siding linked to BNSF for material delivery. A $3.5 billion track and systems contract was issued. Construction begins no later than December 15, 2026. California High-Speed Rail will operate on 25,000-volt AC power. The system uses the global gold standard 2 times 25 kilovolt configuration. The overhead contact system references French TGV catenary technology. Auto-tensioned compound catenary maintains constant wire tension. The system handles temperatures from 25 to 120 degrees Fahrenheit. A messenger wire of stranded bronze runs along the top of the system. This wire is tensioned to over 11 kilonewtons of force. The contact wire is hard-drawn copper or copper-silver alloy. It hangs below the messenger wire where the train's pantograph touches. Contact wire height above the rail is 18 feet 9 inches. In tunnels, this drops to 17 feet 4.7 inches. The distance between messenger and contact wire is 3 feet 7 inches. Catenary masts are hot-dip galvanized steel poles. They are spaced at maximum 210-foot intervals on straight track. Spacing decreases on curves for precise wire geometry. Mast foundations are drilled concrete shafts designed for seismic loads. Cantilever arms extend from each mast to support the wires. Droppers hang at regular intervals to support the contact wire. Auto-tensioning counterweight devices maintain constant tension. These devices compensate for temperature changes automatically. Traction power substations are spaced every 30 miles along the route. Each contains 3 power transformers for converting grid power. 2 independent high-voltage supply circuits provide redundancy. Switching stations sit midway between substations at 15-mile intervals. Paralleling stations with auto-transformers boost voltage every 5 miles. Phase breaks separate electrical feeding areas from different sources. The entire system is designed for reliable high-speed operation. A total system outage is nearly impossible with this redundancy. Every component is engineered to handle the demands of high-speed trains. The electrification system brings 25,000 volts to every inch of track. The automatic train control system is based on European ERTMS principles. This technology is adapted for United States regulatory requirements. In-cab signaling provides primary speed indication to the train operator. Trackside signals exist only as a fallback safety system. Automatic train protection prevents trains from exceeding safe speeds. Positive train control integration meets federal safety mandates. Track circuits provide train detection and broken rail detection. Transponders called balises calibrate train position along the route. Computer-based interlockings govern all junctions and crossovers. The system supports bidirectional operation on both main tracks. A dedicated radio network enables constant communication. GSMR Railway Radio provides exclusive spectrum allocation. A fiber optic cable runs the full length of the corridor. Wayside equipment includes seismic detectors for earthquake safety. Wind speed instruments monitor conditions that could affect trains. Impact sensors detect any roadway underpass incidents. All sensor data feeds to a centralized control facility. Operators monitor the entire system from a single location. Split-second decisions can be made to protect passengers. This invisible infrastructure makes 220 miles per hour travel safe. 4 initial stations will serve the Central Valley's cities. Merced, Fresno, Kings Tulare, and Bakersfield share a unified design. Foster and Partners and Arup created the futuristic station architecture. Metal canopies rise 80 to 90 feet tall at each station. These canopies draw in fresh air while shielding passengers from the sun. Metallic bronze and matte white louvered volumes define the aesthetic. Wood and stone walls add warmth to the interior spaces. Fresno will be the first purpose-built high-speed rail station in America. It is located downtown at H Street in the heart of the city. The restored 1872 Southern Pacific Depot is incorporated. This Queen Anne-style building is on the National Register of Historic Places. 3 of 4 stations feature raised platforms for train boarding. So Fresno uniquely has ground-level platforms. Parking accommodates up to 3,390 cars at stations. 2,580 bicycle spaces encourage sustainable transport. The stations connect to Caltrain and BART in the Bay Area. Metrolink and ACE provide additional regional connections. Amtrak San Joaquin's integrates with the new high-speed service. Each station becomes a hub for California's transportation network. The architecture represents a new standard for American rail stations. These stations will welcome millions of passengers each year. From the moment you arrive, the future of transportation is visible. The combination of technology and design creates an unforgettable experience. California high-speed rail stations are gateways to a new era. And this is how America builds world-class transportation infrastructure.